Today we're going to talk about what's called a two-sided significance test. If you think about it, up to this point in time, I'll call this the old stuff, the hypotheses that we've been dealing with are things like this, HO and HA, where maybe mu equals 10 and mu is less than 10. And we did the assumptions and so forth, but as we proceeded through the problem, at some point, we drew a picture of a normal distribution. And when we drew this picture, we had mu equals 10 in the middle. And since our HA was that mu is less than 10, and maybe we had an x bar of, say, 9.7 or something, we drew x bar to the left of 10, and then we shaded an area that was more extreme than x bar equals 9.7. And this area that we shaded in was called the p-value of our test. Okay? This is an example of a one-sided test because the alternative hypothesis is only less than. Okay? It could have been something like this. We could have had HO where mu equals 10 and HA where mu is greater than 10. And then maybe we had an x bar of like 11.2 or something. And when we drew the normal distribution, here's what we would do. We put mu equals 10 in the middle. We'd mark off our x bar of 11.2, and we would shade above that. Again, the area that is as extreme or more extreme than where our x bar takes place is the p-value. Again, this is another one-sided test because your alternative hypothesis is that mu might be greater than 10. Okay, so what are we going to do today? We're going to do problems where you have HO where mu equals something and HA where mu does not equal something. And when you see this kind of alternative, it's called a two-sided alternative hypothesis or a two-sided significance test. Okay? So the question is, how do you spot a problem like this? How do you read a question and know that it's going to be two-sided instead of one-sided? Well, it's always hiding in the language. So let's take a look at this problem here. The calcium level of blood in healthy young adults it varies with mean 9.5 grams per deciliter and standard deviation of sigma equals 0.4. Okay? So we have a standard deviation given to us. We have a mean that's been told to us. Our mean is 9.5. Okay? A clinic in rural Guatemala measures the blood calcium level of 160 healthy pregnant women during their first prenatal visit. So N is 160, that's our sample size, and their blood level's been measured. And the mean of this 160 people is 9.57 grams per deciliter. Okay? Is this an indication that the mean calcium level in the population from which these women comes from differs from 9.5? And there was the key language when they said the word differs. The question did not indicate a direction of the relationship. Didn't say, does this X bar tell us or indicate that the calcium levels in the blood were higher than the mean of 9.5 or lower than the mean. They just said differs from. So when you hear the word differs from, that's kind of how you know that the alternative is going to be not equal to 9.5. All right, so let's perform the test. So the first thing you do always is you write down what your assumptions are. So our assumptions in this problem, this is, first off, I should indicate, this is a one sample, sorry about that. This is a one sample z-test for mu, for means. And that's an expectation. Every time you do a significance test, you should title what test you're performing. So first, an SRS, which the problem said there was an SRS 160 people. Check. Secondly, the test for independence, which says that the population has to be greater than 10 times the sample size. It also tells us that we know sigma of x bar is equal to sigma of x over the square root of n. So that's checked. There's probably more than 1,600 people in Guatemala. Okay, and then lastly, we got to check for normality. But we luck out here, and the reason we luck out is because n's greater than 30. Since n's greater than 30, that implies the central limit theorem tells us that the distribution of x bar is approximately normal. All right, so we have all three of our assumptions checked off. We're ready to proceed. Okay? The next step is to draw a picture. So we know we can draw a normal distribution. We know we can put what HO tells us in the middle, so that would be mu equals 9.5. And then we have an x bar of 9.57. So we'd like to just mark this off on the picture somewhere. The problem is we're not quite sure if it's close to 9.5 or not. To answer that, we need our standard deviation. So sigma of x bar is going to be 0.4 over the square root of 160. So let's go get that number. 0.4 divided by square root 160 gives me about 0.0316. So there we go. We've got 0.0316. Now, while we're at it, we know we're going to need to get our z-test statistic. So we might as well just calculate that right now and be very precise. So z equals 9.57 minus 9 over 0.0316. Or minus 9.5, sorry. 0.07 over 0.0316. Well, you can see this is more than 2 standard deviations away. Let's just actually divide that and get an exact number. 0.07 divided by that answer there, and we get 2.213. So we are 2.213 standard deviations away. That's considered to be far. So here we go. Here is x bar equals 9.57, or z equals 2.213. And I can shade in that area that is more extreme than x bar equals 9.57. Finally, here's where we get to use the fact that HA, the alternative hypothesis, is that mu does not equal 9.5. This is where that has a consequence. What you do is you use the symmetry of the normal curve. We know that our x bar was 2.213 standard deviations above the mean. We now go over here to z equals negative 2.213 standard deviations below the mean. Okay? And then we shade in that area also. So the final thing then is to calculate the p-value. But the p-value now is this area here plus that area. It's those two areas combined. Okay? So I need to get the area of one tail and then double it. So I'll go do that by doing the following. Second distributions, normal CDF, a z-score of 2.213, comma some massive number, comma 0, comma 1, because the standard deviation and the mean of the z-scores is 1 and 0. We hit enter, and we get an area of 0.0134. So that's what this area is, 0.0134. And you have the same area over here on the other side, 134. So we're done, basically. Our p-value then is just simply 2 times 0.0134, or 0.0268. The meaning of this p-value is this. This is the probability of observing an x bar of 9.57 or something more extreme, right? And then also plus the probability of observing an X bar that's 2.2 standard deviations below the mean or more extreme. So this is sort of like two areas added together. All right, in either way, what you'll notice is 0.0268 is less than alpha equals 0.05, which is usually our gold standard for making decisions. What do we say? We say since our p-value right here, 0.0268, is less than alpha equals 0.05, our z-test statistic is significant, and there's enough evidence to reject HO in favor of HA. And we can conclude that for this population, the mean amount of calcium measured in grams per deciliter is different from 9.5 grams per deciliter. So you have to interpret this, not just say reject HO in favor of HA, but you need to say it in context. Now, you'll notice in this problem, we used alpha equals 0.05. Okay? What I'm going to ask you to do now is compute a 95% confidence interval for mu. So let's write down what our confidence intervals for means look like. They look like this. It's, okay, so it looks like this. X bar plus or minus z star sigma of x over square root of n. Couple of reminders. This whole term here is called your ME, your margin of error. Okay? And then this term here is called, that's sigma of x bar. That's the standard deviation of our sampling distribution. Okay? Z star, you know, that's related to whatever the level of confidence is. So for 95%, it's 1.96. Standard deviation of the population was 0.4. Our sample size is 160. And we're going to add that and subtract it from the x bar we had, which was 9.57. So here is our confidence interval. I guess a quick comment, just in case, about getting 1.96. So you could do is draw a normal distribution. And remember, this is a 95% confidence interval, so I'm going to shade the middle 95% of area. And then we just think about it for a second. We say, oh, well, what's in the tail? Well, the tail would be 1 minus 0.95 over 2. And we know that because if this is the middle 95% of area here, then this tail out here, this tail plus this tail together, has to be 5%. Right? How do I know that? Because it's 1 minus 0.95. I divide by 2 because of symmetry, and I figured out that each tail has a tail area of 0.025. So now, if you want to just use inverse norm, that'll do it. Do inverse norm of 0.025 and watch what happens. So second distributions, number 3, inverse norm, 0.025 equals negative 1.96 or 1.96. So that's how you get that to work. This will give you negative 1.96. You just have to remember that you're going to put the positive version of that up into here. Okay? Now, you can type this into your calculator and get 2 numbers and get the confidence interval. But watch what else you can do. In the calculator, if you press stat and you go over to tests and look on this list, look at number 7. It says Z interval. So that's what you're going to select, number 7, Z interval. And you'll have 2 options, data and stats. Make sure it's on stats. Highlight stats and hit enter so it becomes bold. Okay? And then what we do is we type in our information. Well, our standard deviation in this particular problem was 0.4. Our x bar was 9.57. And our n was 160. And then the confidence level is just a percent confidence interval you want as a decimal. So in our case, 0.95. Oop, I pressed the wrong button there. Hold on. 0.95. There we go. Hit calculate. And there's your confidence interval. 9.508 to 9.632. Okay. So our confidence interval, our 95% CI, is 9.508 to, hold on a minute, let me just see what that was, 9.632. Okay, now here's what I want you to notice. I want you to make this connection. When we did the significance test, we rejected HO in favor of HA. We said that X bar equals 9.57 was so far away from the mean of 9.5 that we're going to reject the mean of 9.5 because the p-value was only 0.268. Notice this confidence interval. Okay? This confidence interval does not catch HO, or the statement that mu equals 9.5. You should expect that. Okay? If the test rejects HO in favor of HA, then the confidence interval will not catch what HO is telling us, or not catch the claimed mean that we've been given. It's just a warning. This idea of using the confidence interval to check if a significance test has a significant or non-significant result only works when your alternative hypothesis is that mu does not equal to. It has to be a two-sided test. Otherwise, this confidence interval idea doesn't work so nicely.